This is Science Max, experiments at large. Science Max!
Oh, hello, Science Maximites. We've got a lot of work today, so I was just getting prepared. You know, taking something flimsy and making it strong, that's what scientists and engineers do every day. And it's also pretty fun. You take something that's not that strong, and by the way you build it or put it together or change its shape, it suddenly becomes a lot stronger than you think it was. So I thought that's what we should do today on Science Max Experiments at Large. We should build something. So we're gonna build an arched bridge, and we're gonna build it out of sugar cubes. So here's what you need. You need some sugar cubes, you need some sandpaper, and you need some modeling clay. So first, you want to make some abutments out of your modeling clay. What is an abutment, you ask? It is this. They distribute the force laterally from one side or the other. I like to use this. This is half a roll of duct tape. And so it fits in just like that, and you see, it's a perfect arch. If you just take sugar cubes and you try to stack them into an arch, it's not going to work because the sugar cubes may not even fit all together, and you can see only the bottoms are touching. I take up the guide and it all falls apart. So here's what you do. You take your sandpaper and you change the squares into trapezoids, and you start sanding down your sugar cubes into trapezoids. Basically, you want one small side and one long side. Thin at the top, wide at the bottom, or wide at the top, thin at the bottom. It's a trapezoid no matter which way you hold it. Put it on the bridge and see. And as you go, you will see if you're doing it right, there will be no gaps. If you go to the Science Max website, there will be a guide that you can use to help you make the sugar cube bridge. So you don't have to spend as long as I did making this one. And then the most important part is the keystone. That's the one that fits in right at the top, just like that. And when it does, you can take away the guide and it stays up. Isn't that cool? It stays up without any glue, without any mortar, all based on the shape of these sugar cubes. The cool thing is, it'll hold the weight of a whole car, provided you have a very, very small car. The reason why it works is because the weight is distributed along the arch into the abutments and down into the ground. That's what makes an arched bridge so strong. And that's what we're gonna do today. We're gonna max out an arched bridge. So I think I'm gonna need some help though. Maybe Sonia from the Ontario Science Centre. She really knows her stuff. Yeah, I'll go there and I'll see if she's busy. All right, come on, let's go. Hey, Sonia.
Hi, Phil. How's it going?
It's going good. I was wondering if you could give me a hand with something.
Okay. What's up?
I'm building, well, it's easier if I show you.
All right.
Do you mind coming back to Science Max headquarters? We can take the portal.
But that thing doesn't always work.
Oh, it is fine. Well, I mean, that worked just fine. Uh-oh, it usually makes a beeping when I do. Oh, it's out of batteries. Oh, I told myself, Phil, charge the remote before you leave the lab, and then I.
Where have you been? Breathe.
The remote ran out of batteries, so I had to run the last 3 kilometers.
It's all right.
Because
You made it.
Long story. So the sugar cube bridge, you had a chance to look at it, right?
Uh-huh.
This works on any scale, right? It should, no matter what size arch, it should be the same, right?
Definitely.
Good, because what I want to do is use these abutments, but go to these abutments.
Oh.
So I'm gonna start the bridge here, and I've already created a thing that we can use to put the sugar cubes on as we go up, so that we can make sure that it becomes a
Phil,
perfect arch. Yeah.
Do we have enough sugar for this?
Yep. I got tons of sugar.
Wow.
Yeah. So I think we're gonna need some glue because it's gonna be really hard to get these to stay.
Yep.
To stay right
on.
there without a little bit of glue. We're gonna make a giant arch, maybe some walls, and we'll see what happens.
Let's do it.
oops, an egg. Now you might think of eggs as kind of flimsy, and they do break pretty easily, but eggs are actually stronger than you think. It's because they're, well, egg-shaped. You see, the top of the egg is like a little bit of an arch, and the bottom of the egg is also like an arch. And arches distribute the weight, just like they do in a bridge. Here's how you can experiment with how strong eggs are. First, you want to get a pair of gloves to protect your hands from the shell, just in case anything goes wrong. You should also tell an adult that you're doing this experiment because if it does go wrong, you're gonna have some mess to explain. And also, you should probably put on some safety glasses. Now, here's what you do. Take your egg and carefully put it in your palm just like that. And put it against your other palm, and you're gonna push in directly on either side of the egg. Start pushing harder and harder. You can even lace your fingers and press even harder. And if you do it right, the egg won't break. Pretty amazing, right? So, just how much weight does an egg hold? Can one egg support my entire weight? Let's find out. I'm gonna lift my weight up like this and lower myself down. And no, cannot hold my weight. Can my weight be supported by 2 eggs? Oh, nope. Phil's weight, 4 eggs. Oh, I thought they were gonna do it. Nope. My weight on 8 eggs. Huh? My weight can be supported by just 8 eggs. Science! Whoa, careful. Sonia and I are on a quest to make a maxed out sugar cube bridge. The reason why an arch works is because the weight, or the load, of whatever's on top of the bridge is carried outward along the curve of the arch to the abutments at each end, which carry the load and keep the ends of the bridge from spreading out. No matter what you build your bridge out of, sugar or stone, the science stays the same. Sonia and I are building a much larger bridge out of sugar cubes. We're using glue to help the sugar cubes stay together, just like stone bridges use mortar. And when we're finished, it was pretty impressive. A massive sugar cube bridge, right? High fives for that. The moment of truth comes when we take out the support and... Yeah! It works! Okay. Giant sugar cube bridge. So do you think it'll hold some weight?
I think it definitely should, because right now we have an arch, perfect arch, and the weight is being distributed to the sides, the base,
So that's what it's for, right? We can put weight on there?
we can definitely put some weight.
1 to start?
Let's start off with 1.
Okay.
And let's see how it goes.
All right.
Here we go. All right.
Yeah, 1 book, yeah! All right, sugar cube bridge,
1 book.
2 books.
Are you nervous?
Yeah! Sugar
books.
cube bridge, 3 books.
3 books.
Oh, that was great. It held up 3 books.
3.
Well, technically it held up 2 books and broke on the 3rd. So it's kind of still far from how much weight we want to hold because we want to cross it.
We definitely want to cross it, so that means we need something bigger and stronger. The cube works.
You're right, because the cubes are great because that keeps the science the same.
Yep.
Right? So something cubular. The milk crate, really?
Definitely, I think we should use those. It's a cube.
It is a cube. A whole bunch of milk crates, and we'll see what we can do.
I think that sounds great.
Awesome. Whoa. This is a Prince Rupert's drop. It's a piece of glass that has a long snaky tail and a bulb at one end. So what's so interesting about a glass tadpole? Well, I'll show you. And remember, this is just glass. Oh, Prince Rupert's drops are very strong, almost as strong as steel. It's all in how they're made. Molten glass is dropped into cold water. What happens is the outer part of the drop cools off first, leaving the inner part still hot. When the inner part eventually cools, it contracts, pulling everything in tighter and tighter, keeping it under a lot of tension. And because it's round, the force you put on it is distributed all the way around, just like the force is distributed on an arched bridge. Until you get to the tail. Just the tiniest break in the tail, and it explodes. All that energy is released in a chain reaction. Why it's so strong you can hammer on one end, but explodes when you break the other, puzzled scientists for centuries. But now we know it's all in how it's made.
The Wizard Academy. All you have to do is demonstrate true magic, and you will be granted entry.
Send in the next applicant.
Okay, don't let them see you. Don't let them see you. Okay, magic smoke. And here we go. Big entrance.
Behold, it is I, Overwhelmo.
You again.
I only have to demonstrate magic one time, and you have to let me into the Wizard Academy. And last time does not count. So prepare for your mind to be boggled and your eyes to also be boggled, because I shall do a trick. I will just get to it. Here is a book, behold! And now, feast your stupefaction as I produce another book, ha-ha! And then 2 or 3 more times, behold, that's good. Behold! And now, look upon the wonderment as I stack these books on top of each other, like this. And now, feast more stupefaction as I cleverly move the books off the table. And now comes the magic word. Now, I say the magic word. The magic word! And behold, the book is levitating. It is completely off the table. I have done it. Magic!
No.
No?
Not magic, that's science.
But the book is levitating.
No.
Look at it, it's not even touching the table.
No, it's being supported by the books below because of the center of mass.
Preposterous.
I'm afraid it's very posterous. Each book is balanced on the one below in a way that the center of mass is behind the edge of the book below. And the entire stack's center of mass is behind the edge of the table. So it may look like magic, but it's science.
So, I can't get into the Wizard Academy?
No, I'm afraid not.
Good. Alakazam! You will rue the day that Overwhelmo did not. I will return, and then you will see. Oh, ow.
Sonia and I made a large bridge out of sugar cubes, and it didn't hold much weight. So now we're going to try making another arch bridge, but instead of sugar cubes, we're going to use milk crates. There we go. I've made some abutments out of giant crates, and this is where we're going to start our bridge. And they start there, and it goes in a big arch, but we're going to be using...
I brought milk crates!
Milk crates! High fives! High fives! So we start our bridge. This is a straight line. It's not an arch.
It's not an arch.
But it's clear we have a problem. Okay, ready?
That didn't work, Phil.
It's like we're back to the beginning again. So this is like 2 straight
We
lines.
have 2 straight lines,
It's
yep.
like a triangle.
We need an arch, so we're gonna need a support.
Sonia and I build a support to help us make a curve the milk crates can follow. But after we finish stacking, there's a problem.
It doesn't look very solid.
Yeah, it doesn't, does it?
Here.
Oh, yeah. Because there's a gap at the top of all of them. Look, that one, there's a gap. There's a gap there.
There's a big
a
one
gap
here.
there.
It's
Well, I
not
mean,
making our bridge very solid.
There's only one way to find out for sure,
You can try it.
is to pull this out and see if it stands up.
Let's do it.
Okay. So, didn't stay up.
Didn't stay up.
Okay.
That's all right, though.
I'm not sure why it isn't staying up. Like, the sugar cubes were cubes.
That's a cube,
Milk crates are cubes.
but we did change the shape of the cube.
Oh, yeah! If you remember, when I first built my sugar cube bridge, it didn't work with cubes. You have to sand the cubes down to make them into trapezoids. You can't build a perfect arch out of cubes. So they were tall, wider here and then narrower there so that they had... Oh, so that's the problem.
Yep.
So I could, like, cut it? I could cut it. I could cut it.
You could.
I could cut it.
That's gonna take a long time, though.
If we cut the milk crates into trapezoids, everything will work, right? Right? We take a milk crate and with the right safety gear, we cut it so we can reshape it into a trapezoid. Good. And it works, but it's gonna take a long time, isn't it?
Definitely. So how about this? I have an idea. So remember when we did the experiments and we had lots of V gaps?
Yeah?
How about we put some wooden wedges into those gaps to make it one secure structure?
So it was sitting like this.
Exactly. So what we're gonna do is insert wooden pieces right here, so we'll fill those gaps.
I get
and
it.
we'll make it one secure structure.
Instead of cutting all of our milk crates, we can keep the milk crates.
Yep.
And they can be solid and we just add to it rather than take away.
Taken away, exactly.
That is a smart idea. Okay, let's make some wedges.
All right.
Oh, hey, how you doing? Let me guess, you want to build a strong structure, something that'll stand the test of time. Well, you know you gotta use the right kind of shapes. Look at this, a square. Now, squares have gotta be strong, right? Well, maybe. Maybe if you press straight down on it, but watch as I push to the side. Oh no! The thing that I have built is now collapsing because squares aren't in fact strong after all. If only I had listened to Sal's sage advice. Yeah, squares aren't gonna cut it. Fortunately, there's a shape that's strong in all kinds of ways. A triangle. Okay, so you heard of triangles before, good for you. But look at this. You can push down from the top and it doesn't move, or you can push from the side and it doesn't move. Triangles are awfully pointy. How do I build with them? Observe! Ha-ha! Triangle here, triangle there, platform on top. And watch. No matter how I try to shift it, it stays solid. And check this out. Triangle here, second triangle there, and a third triangle shape here. That's like 3 triangles for the price of 2, huh? That's a good deal. So there you have it. The triangle, one of the greatest shapes to build with.
This is a house of cards, and if you've never built a house of cards, you should definitely try. Try, because it's not easy. What you need to do is you need to make triangles with the cards. If you do it just right, they'll stay up. Then you take another pair of cards, like that. You take another card, and you put it on top. And it stays up. Keep on building by making triangles and putting another card across the top like a roof. Then, when you're ready, you can start to make a second layer. It takes a lot of patience to make a house of cards. But with enough patience and really steady hands, you might be able to finish it. There we go. Ha-ha, a house of cards. Now, let's max it out. Backing away slowly, backing away slowly. To build our maxed out card house, the Science Max build team and I used large pieces of foam insulation, which were super light and easy to work with. Once we set up the first layer, we needed to bring in a scissor lift so we could keep building the next layers. By the time we got to the top, our card house was 10 meters tall. Yeah! Giant house of cards! And now that I've built a giant house of cards, what do I do with it? I knock it down. Science! I'm gonna build it again. Sonia and I are rebuilding our milk crate bridge. Since cubes don't work if you're trying to make an arch, and changing the shape of each milk crate would take too long, we're using wooden wedges to fill the gaps at the top of the milk crates. Once we get the wedges in, the milk crates have support at their tops, and they make a perfect arch. Are you ready?
I'm ready.
All we have to do is pull the wooden thing out, and if it holds up on its own, we've done it. We pull out the support, and it stands! It works! The
bridge supports itself. Now it's time for the final test.
We try to walk on this bridge.
So we spent some time making sure our bridge was safe. We added a crash mat and
We built a second arch
We sure did.
so that it's a little bit wider, and it feels very solid. So the only thing to do now is to test it.
Test it out.
You gonna do it?
I absolutely will.
All right.
Sonia puts on a helmet and gives it a try. And sure enough, it works.
Yeah! Milk Crate Bridge!
Milk Crate Bridge!
Milk Crate Bridge! Milk Crate Bridge! Milk Crate Bridge! Woo-hoo-hoo-hoo! Science Max experiments at large. Milk Crate Bridge!
Yay for science!
High five! High five!
Greetings, Science Maximites. I am Phil McCordick, and this is Science Max Experiments at Large. Today, we're going to be experimenting with the balloon-powered car. Here's how it works. Woohoo! It all has to do with Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
We don't have to do this now. This is all for later. We can build the cars first, and then we can, let's go over here. So how do you build a balloon-powered car? Well, I suggest you be Science Maximites, because there's any number of ways you can build a balloon-powered car. You do not have to follow my design. You should come up with one of your own. It may even be better than the one I built. But I will give you some tips, though, that make it a lot easier. First of all, you need something to stick your balloon on that has an opening on it. I used a turkey baster for this car. I just pop the top off, and remember to tell an adult that you're using the turkey baster. And then you stick the balloon on there, and it allows you to attach something to the car, and it also makes it easier to blow up the balloon. You can use any number of things, even just any kind of tube that you find lying around. It helps you attach the balloon to the car, and it helps you blow up the balloon way easier. The other thing you should think about when you make your balloon-powered car is how you're going to make the wheels roll. Once you've decided on the base of the car, you could use anything, even just a piece of cardboard like this. You can do your wheels in two ways. The first way is to attach the wheels to the axle. This is how I made the axle of this car. I used a shish kebab skewer, and I stuck it inside a straw, just like that. And then I attached the lids to the shish kebab skewer. So the lids and the shish kebab skewer are attached, and they rotate in the straw. That's one way to make the wheels turn. The other way is to tape down the axle or whatever you're going to use and have the wheels spin around on the axle. Two great ways to make your wheels turn, and it really kind of depends on the wheels you're using. You can make your own design and keep refining it and making it better and faster, or do what I like to do and make a whole bunch of different cars. So we've got this one. This one I made out of paper plates, and this is a snorkel. Awesome. This one is the rock car, because there's a rock on it. I've got the dragster model. It's a long broom handle, and it might not work that well, but who knows? And this is my favorite design. It's made out of waffles and an ice cube tray. This is why I make a whole bunch of different cars, because I can race them.
Sunday, Sunday, Sunday at the Science Maxidrome. It's the balloon-powered car winner-take-all drag race of awesome.
First up, the Eliminator.
Woohoo! Better late than never, it's the Procrastinator. Crushing the competition, it's the Terminator. Feel the chill of the refrigerator.
All right.
And last but not least, the Regurgitator.
Well, when you build your balloon-powered cars, you can figure out what worked or what didn't work and try modifying your designs to make them work even better. That is science. And now we're gonna max it out because this is Science Max Experiments at Large. So we're gonna take that small balloon-powered car that we just built and we're gonna make it much, much bigger. I'm gonna go to the Center for Skills Development and Training and we're gonna use the science behind the small balloon-powered car and we're gonna make it big. That science is Newton's third law, but there's plenty of
third law.
no, there's,
For every action,
there's
there is
plenty
an
of time
equal
for this
and
later.
opposite
We're not doing this bit now. We're doing that bit in a minute, so we can. No, I said we're doing it later. We're doing it later. Here. Whoa. Hi, Sarah.
Hi, Phil.
This is Sarah, and she's got a master's degree in physics from McMaster University.
That's right.
And we're gonna be talking about Newton's third law. Oh, look out, duck! Sorry. There was a sign that kept coming in. Never mind. Newton's third law. Well, what is that?
For every action, there's an equal and opposite reaction.
Right, so how does that work with our balloon car?
Ah, cool. Okay, so if you blow up the balloon, what's gonna happen when you release it is the air is gonna push out with a certain force, which in turn is gonna cause the cart to move forward with the exact same force.
Yeah, works great. So how come it doesn't work with my rock cart?
Ah, wow. Well, actually, it did work. So the balloon still pushes with the exact same force, which causes the cart to have the exact same force push forward, but your rock is really heavy, so you probably didn't see it move.
Oh, so a lighter cart works better with the same amount of force.
That's it.
Well, there you go. Newton's third law. What?
Newton's third law. For every action, there is an equal and opposite reaction.
I'm really starting to dislike that sign.
Phil, are you okay?
Yeah, I'm fine.
Our small balloon-powered car works because of Newton's third law. For every action, there's an equal and opposite reaction. The air pushing out the balloon this way pushes the car with the same amount of force this way. So, in order to max it out, the plan is just to get a bigger wheeled cart and a much bigger balloon. So, everything should work out the same.
Okay, so sorry. Oh, I thought what we would do is in order to max out the balloon-powered car, what we need is a cart to start with, and then I ride it. And we have a giant balloon, and then I go.
Do you have a giant balloon?
Ha 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 ha! Giant balloon! So, step one, Sarah blows up the balloon.
Okay.
Wait. Use this air compressor, it'll probably be a lot faster.
Sarah and I get to work blowing up the balloon, and it takes a long time. A very long time.
Okay, human-sized balloon-powered car test. Take one. All right, Sarah?
You got it?
Yeah. Okay, let it go.
Okay, go!
Let it go.
I did.
You did let it go.
I just let go.
Nothing is happening.
It's not coming out fast enough, and you're a bit too massive. I don't think it's gonna work like this.
Really?
Yeah.
Okay. Balloon-powered car test 2. No fill. I'll just take it. What happened?
I don't think it worked. The balloon popped. Phil, are you okay?
This is why you wear protective eyewear. Yeah. So, that didn't work.
No.
No. Should we get another balloon?
I think we need something else.
Okay, well, the air coming out of the balloon just didn't have enough force, so.
We need the air to come out with more force.
Yeah, do we get, what, a bigger balloon?
I don't think that's gonna work. I don't think it's that. I think we need something with compressed air.
Oh, like a scuba tank or a...
Fire extinguisher, something like that. Yeah, that's what we need.
Okay, sure. Well, we can... All right, so I don't know if that's safe to do that, so we'd have to build like a cage or
yeah,
something?
I don't know if it's gonna work on this.
All right, well, back to the drawing board. So
Okay.
what we should do is we should get
We need to find these tanks.
get the tanks, and then we make like a frame out of aluminum or something.
Okay, that could work.
Yeah,
That's
they
a
can
good
hold the
idea.
tank, so
Yeah.
they're safe. And then what we should do is...
Who was Isaac Newton? He was a mathematician and probably #1 on the list of top scientists of all time.
Albert Einstein said, Isaac Newton was the smartest person that ever lived. You've got to be special if Einstein is calling you smart. Newton's 3 laws of motion was a huge idea, but did you know Newton also came up with the idea of gravity? The famous story is that in 1666, Isaac Newton was sitting under an apple tree when he watched an apple fall and wondered why. Hey everyone, I just invented gravity, which was a big relief because up until then, everyone was just floating around. Okay, so it didn't happen like that. He didn't invent gravity. He gave a name to this invisible force and then described how it works. Not only did it make things fall down, but it was the same force that kept the moon circling the Earth and the Earth circling the sun. And he invented a new kind of math to explain how. We now call it calculus. See? I told you he was smart. He's very smart.
This is hydrophobic coating. Hydrophobic literally means afraid of water, but it's not actually afraid of water. The chemistry of a hydrophobic coating prevents water molecules from penetrating anything you spray it on. You can get this stuff at the hardware store, and if you want, be science maximites and get an adult and think of the coolest thing you could spray with hydrophobic coating. I like to use things that do not go well when you put them in water, like tissue. Yeah, doesn't look great when it gets wet. Here's a tissue coated in hydrophobic coating. Huh? Weird. Or it works the same with a paper towel. Paper towel in water, paper towel covered in hydrophobic coating, stays dry. Or how about a dinner roll? Dinner rolls really don't like water. See? Gross. But a dinner roll coated in hydrophobic coating? Weird. Just don't eat it. Now, it's time to max it out. I have coated half of my lab coat in hydrophobic coating, and the other half I have not. Hydrophobic coating, regular lab coat. Half of me is wet, and half of me is dry. What's more, half of my outfit ended up being wet and half dry because the lab coat was protecting my outfit from getting wet. Now it's time to max it out even more. We have coated my entire outfit in hydrophobic spray. My shirt, my pants, and my lab coat. The pants have been taped to rubber boots, so no water's getting in there. And my shirt has been taped to my pants, so no water's getting in there. So here's the question. Can I get into the pool and out of the pool and stay dry? Let's find out. In the pool, out of the pool, and I'm still mostly dry. Now here's what really happened. I got into the pool, and I realized I should have duct taped the pocket, because all the water went in there, down into the rubber boots, started filling up the rubber boots, and now my entire leg is full of water because the hydrophobic coating isn't letting it come out. So the hydrophobic coating isn't keeping the water out. Now it's keeping the water in. Let's take a closer look at Newton's third law.
Newton's third law. For every action, there is an equal and opposite reaction.
Okay. All right, let's watch it back. When the sign hits me, I exert a force on the sign in the opposite direction. That makes the sign stop moving. It also exerts an equal force on me, causing me to fly off in this direction. Now, if I was to push this sign, I'm not only pushing the sign this way, but my feet are pushing against the ground in the opposite direction. It's, well, it's really easier to see if I'm not standing on the ground. No, hold on. Okay, so, huh? Oh, okay. So now that I'm hanging, watch. I push on the sign, but when I exert force on the sign to make it go this way, I go that way. Well, actually, it doesn't work as well because the sign isn't as heavy as I am. So wait, I have this over here. This is a barrel, and it has stuff in it, and it weighs as much as I do. Okay, so watch. If I push on the barrel like that, I go away from it as much as it goes away from me. So, there you have it. Newton's
third...
No, hold on. Newton's
third law.
Newton's third law. Okay, go.
Newton's third law. For every action, there is an equal and opposite reaction.
So, using a giant balloon to push me on a cart didn't work.
What happened?
The plan now is to use the compressed gas cylinder. Just like a balloon, these cylinders contain a lot of air. If we get a cart and put a gas cylinder in a cage for safety on the back and open the valve, the escaping air might have enough force to push me.
This is 2 cubic meters of air. If we were to put it in a balloon, the balloon would be this big. But if we compress the air, we can fit it all into one of these, a steel tank. This is what we're going to be using next for our air-powered car. Got it?
Yep.
All right.
Good.
So Sarah and I have been hard at work, and we've built the air-powered cart. We can't call it a balloon-powered cart anymore because now we've got a compressed air tank, so it's not a balloon that powers it.
Exactly.
Okay, so I'm gonna sit on here, Sarah's gonna turn on the tank, and I'm gonna go. And before we do this, we should say, do not, under any circumstances, try this at home. We are trained professionals. You ready?
I'm ready.
Okay, high five first. Okay, now we do it.
Okay, so before I turn the tank on, make sure your feet are down and the brakes are on.
Gotcha.
Don't take them off till I say go.
You have got it.
All right.
Ready?
Okay.
Yeah!
It worked.
Yeah, it did work, but I feel like it could work better.
You want to go faster?
I do want to go faster. This reminds me of the rock car.
Yeah.
Where we didn't have a big enough balloon.
We need more force.
We need more force. So should we get a bigger tank?
Let's get more tanks.
More?
Tanks, more force. You're gonna go faster forward. Newton's third law.
Newton's third law, high five. All right, let's do it.
All right.
Whoa. This is Newton's Cradle, and it's a really cool toy that demonstrates all kinds of laws of motion, including Newton's third law. What you do is you pull this one ball out, and when it hits these balls, they exert force on that ball to make it stop moving, but it exerts force on these balls, which travels through the balls and makes this one on the end fly out, like that. Now, there's a lot going on here, but you can really see how the force is equal that you put in and you get out if you use 2 balls. I swing 2 balls up, and 2 balls go out that side. Isn't that cool? Now, it wouldn't be Science Max unless we maxed it out, so come on. Whoa, okay. This is one we built out of bowling balls. Bowling balls, bowling balls, instead of smaller balls. And I think it's gonna work the same way. Let's find out. You throw one out, and haha, yeah, it works the same. Okay, now let's try it with 2 balls. Okay, ready? Wait. And 2 balls, throw them out. And 2 balls on that side. All right, so there you have it. Whoa. Newton's third law. Oh. Ah!
Newton's third law. For every action, there is an equal and opposite reaction.
So our single pressurized tank created enough force to move me, but not very fast. The plan now is to do 2 things. First, we're going to triple the amount of thrust by using 3 tanks. We're also going to use some pipes that lock into each other to give me an initial push. These pipes slide together, and when the air is turned on, the pressure in the pipes will cause them to slide apart, which will push me forward. After that, I use what's left in the tanks to keep going.
All right, now it's time to max it out. I've enlisted the help of a few more Science Max people. Thank you very much, Corey. You'll see now we have 3 tanks of compressed gas, and we've also got this nifty little contraption. How does this work, Sarah?
All right, so each tank is attached to a tube,
Yeah.
and you can see that each tube goes into this one main tube, so when we turn them on, pressure's gonna build up, and we're gonna go forward with more force.
Well, that's great. And Reed is stacking cinder blocks, thanks Reed, up so that will push, the pipe will push against the cinder blocks, and then I'll go
Or it goes
that
forward.
way. All right, well, are you guys ready?
I'm ready.
All right, let's do it. Now, again, I have to say, thank you, Corey, I've got it. This is something you definitely don't want to try at home. We are all trained professionals. We have a physics degree here. We've got TV people that make sure that this is safe. So watch it and enjoy, but please don't try any of this at home. Okay, I'm ready. Sarah, count me down.
3, 2, 1.
Yeah! Woo! Uh-oh. Woo-hoo-hoo. That was awesome!
That was really awesome.
All right, high fives, high fives. Yeah. And it's raining now, so it looks like we're gonna have to stop. So thank you very much for joining us on Science Max Experiments at Large in our episode on Newton's third law.
Hey, welcome to Science Max Experiments at Large. I'm Phil McCordick, and hold on a second, I'm just gonna change. Okay, that's better. Now, where were we? All right, let's go make a boat. So you know that some things float and some things sink, like rocks, or wood, or full water bottles and empty water bottles, or carrots, foam, waffles, screwdriver, playing cards, plasticine, tinfoil, potato, my watch. Wait, that wasn't supposed to go in there.
So how do you make a boat? You make it out of something that floats, right? Well, most boats are actually made out of metal. Tinfoil is metal and, well, it sinks. But if you fold tinfoil into a boat shape, it floats. And boats don't only float themselves, but they can hold people and cargo. In fact, there's container ships crossing the ocean at this very moment that are holding thousands of tons of cargo, and they're all made of metal, which doesn't float, it sinks. So how do boats do it? Are they magic? No, of course not. Boats are science. And here, you can be science maximites. Get some tinfoil and cut it into the same size pieces and fold a couple different shapes of boats and see which one can hold the most weight before sinking. And now it's time to max it out.
But before we do, here's how you can fold your own tinfoil boat in less than 15 seconds. First, take a square piece of tinfoil, then fold it in half. Fold one corner down and the other corner down. Then open it up and ta-da, you're done. If you want instructions on how to fold a more complicated boat, go to our website.
I have a feeling I'm gonna need a few extra lab coats for this experiment. Like I was saying, let's max out the tinfoil boat and find out a little bit more about why boats float.
Okay, well, I'm here at an indoor pool, which is not, I wasn't expecting to be in the pool just yet, but this is where we're gonna build our giant tinfoil boat, so why not? Who's Nia?
Phil, you're wet.
I thought I was gonna come in over there, but I came in on the water sled. I think I had the coordinates wrong. Anyway, this is Husnia, and she's from Let's Talk Science, which is all about science education, right?
Yes.
Just like us. So you're gonna help me max out the tinfoil boat. I think I dropped it in the water. Hold on. Whoa! Up here. Where? Here it is. The tinfoil boat. The tinfoil boat.
Phil, this is a boat?
Well, it looked a lot better before I came down the water slide, but that's the idea, and then we make it bigger. What do you think?
I don't think it's gonna work, Phil.
Oh, well, why not?
Tinfoil is very thin,
Uh-huh.
and it might not hold the shape of the boat.
Well, I still think we should use tinfoil, though.
Why?
Well, because the small experiment was tinfoil, and I bought all of this tinfoil.
Then let's do it.
Tinfoil? Okay, high five. I will, I'll take the tinfoil and you take that, and I'm gonna have to dry off at some point.
Welcome to Shipbuilding for Pirates. I'm Swubby, and I've built some of the finest pirate ships for some of the finest pirates this side of the Caribbean. And I can teach you to do the same. But first, you need to know your basics. Mass and volume. Let's start with volume! But not that kind of volume. Which of these two chests do you think has more volume? Right, this one here. Which of these two balloons do you think has more volume? Right, this one here. Volume is how much space something takes up. Which of these two chests has more volume? That's right, they're the same. But which of these two chests has more mass? Which is heavier? Hard to tell, isn't it? But what if I told you that this one was empty and this one was full of treasure? Oh, loonies. Now, which one has more mass? That's right, this one. These two chests have the same volume, but this one has more mass. This chest has more volume than that one, but this one... My loonies! That chest does not have as much mass. Volume is how much space something takes up, and mass is how heavy something is. And when you look at them both together, you're looking at density. Join us next time on Shipbuilding for Pirates, and then we'll look at how volume, mass, and density work together to make something float. Oh, my precious, precious loonies. Are you all right, my pretties? They can't talk, so I'm not sure what they're saying.
So, Husni and I get to work constructing a large tinfoil boat. Our first design is just sort of a square, folded together out of a very large sheet of tinfoil. Simple, but can I ride in it? There we go. A giant tinfoil boat, just my size. Woo-hoo-hoo-hoo!
I don't know if it's gonna work. It's too thin.
You think it's too thin?
I feel like yes.
Well, what should we do?
Do you want to test it?
Let's test it. Okay, good idea. So here's the most important question. Do you want to test it or should I test it?
No, you test it.
All right, here we go. Putting it in. First test, does it float on its own? Yeah! Floats on its own, no problem. If I just get in very carefully, then it will work fine. You see, if I'm careful about how I get in, no, it's fine. See, if I just get in like that.
Oh my... Bill, are you okay?
Wait a minute. It's sort of, no, that's just air. You know what went wrong? It wasn't boat-shaped. I think if we make it look more like a canoe, because canoes float, if we make it look like a canoe, it'll work great.
No, Phil. We need some support. If we add a couple of structures in between, then we add support to it.
I'll tell you what. Let's make a boat like I want to make and a boat like you want to make, and we'll see whose is the best.
That's a good idea. Okay, let's do that.
All right, let's do it.
Welcome back to Shipbuilding for Pirates. I'm Swubby, and now we know what volume means, what mass means, and that together it can tell you something's density. Now let's find out why things float. Let's say we're out to sea and my treasure chest gets swept overboard. Oh no! But it's all right. It floats because it pushes enough water out of the way, displaces it to carry its mass. But what if my treasure chest had more treasure in it? Well, we're giving it more mass, but not more volume. Too much mass and not enough volume, and it'll sink. Oh no! My loonies! You need more volume if you want to float more mass. And that is why things float. I'm Swubby, and thanks for joining me on Shipbuilding for Pirates.
So, the first version of the tinfoil boat didn't work out too well. Like that. But my idea is to build a tinfoil boat more like a canoe to see if a different shape makes any difference. Tinfoil canoe!
Very Canadian.
Very Canadian. The canoe part, anyway. I don't know about the tinfoil part. So, Husni and I had a bit of a disagreement of why the last boat didn't work.
I thought it was because it wasn't shaped enough like a boat. So this one looks like a canoe.
What I thought is that it requires some structure.
Structure so that it wouldn't fold together.
That's right.
And we'll see how it goes.
All right.
All right, here we go. Did it work?
Nope.
Okay, your idea next. Did you know it's easier to float in salt water, like in the ocean, than it is in fresh water, like a lake or a pool? That's because not all liquids are created equal. They have different densities. This is fresh water, or it doesn't have anything in it. And this is sugar. If I was to put 1 scoop of sugar in this water and stir it around until it dissolves, now this liquid is more dense than before I put the sugar in. Here's an experiment you can do at home using liquid density. This glass just has regular water with yellow food coloring in it. This glass, green food coloring and half a cup of sugar in it. This one has a full cup of sugar in it, and this one has 2 cups of sugar in it. Now, when you do this at home, you'll definitely want an adult to help you because you have to heat the water if you want to dissolve that much sugar in 1 glass of water. I'm gonna put them all in 1 container. You can do this at home, and when you do, I suggest you use a very small container because you have to be very careful when you put the layers in. You can use a turkey baster or a straw. When you put your finger on top, the air pressure will hold the liquid in and you can just drop it in. But these kind of take some time, so I'm going to use the syringe of science. I'm gonna use the most dense liquid first because that's the one that's gonna want to be on the bottom. I carefully put it on the bottom of the container. The next layer, be very careful, and you'll see that the red and the blue aren't mixing because they have different densities. The blue is heavier than the red. We'll add the green, and you can see even when it drips into the red, it comes back up to the top because the green liquid isn't as dense as the red liquid, and the denser liquids push the lighter liquid up. And now we're gonna add the yellow, which of course has no sugar in it at all. And there you go. All the layers stay separate. If you put it on a light, you can really see it. Liquid densities. Now, let's max it out. Ta-da! The longest length of liquid layers. 12 liquids all organized by density. Starting from the bottom, we have honey, corn syrup, chocolate syrup, maple syrup, dish soap, whole milk, water, dyed blue, vegetable oil, extra virgin olive oil, rubbing alcohol, baby oil, and lamp oil. Liquid density. I really want to mix it up, but it took me a long time to make this, so I'm not going to. Our first 2 attempts at a tinfoil boat haven't gone so well. Husnia's idea is to make a tinfoil boat and add some more structure, because the tinfoil just wants to collapse when I get in it. So we start with a large piece of cardboard on the bottom, then we wrap the tinfoil around it and shape it into a boat. After that, we add some supports across the top to stop it from folding in when we add my weight to it. This boat feels a lot stronger than the one I was just in.
I told you.
So how does all of this work?
So we got some support using broomsticks and then some cardboard paper. And then underneath, we have cardboard.
And so how will all of this help the boat not sink with me in it?
Right. The broomsticks will prevent it from folding this way and you won't sink.
Good.
The cardboard will prevent it from folding this way and you won't sink again.
Not sinking is my favorite thing to do in the tinfoil boat. All right, so let's try it.
Let's do
now,
it.
Are you gonna get in this one?
I'll tell you what, Phil. If you get in and you don't sink, I'll go after you.
Deal.
All right.
All right, here we go. It's sort of working. Oh no, water's coming in. It's sort of working.
It's almost working.
Coming in. Uh-oh.
Wow.
No. Another thing I learned is that a very light tinfoil boat can be very heavy when it's full of water.
I don't know if fixing it is in the cards. I think we're gonna have to build another boat. So what do you think we should do?
Let's add more structure.
More structure?
Oh, yeah.
What if we add like a metal rod around the outside and maybe some more metal rods and ribs? And we wrap it all in tinfoil, and you think it'll work?
Let's give it a try.
Let's give it a try.
Don't worry about it. I got this.
No, I get it. I'll get it.
Sure.
Who wants to do an experiment with diapers? Oh! No, I'm serious. You may have a little brother or sister at home, which means you probably know where you can find some diapers. But there are two things you need to remember. First, ask an adult if you can use the diapers for your experiment. And two, only use unused diapers, okay? Okay. So, you take the diaper, and if you cut it, be very careful, maybe get an adult to help you, over some black construction paper, like I have here, and you shake the diaper over the construction paper, you'll see that there's a little powder that comes out. And this is the secret ingredient. This is super absorbent gel. And what it does is it soaks up all the liquid, and diapers are full of them. And you carefully pour it into a plastic cup, like that. Now you can see I have already done it with a number of diapers. It's important to use a plastic cup because it's a little messy, although it's non-toxic, it's totally safe, but it's still easier to clean up by just throwing the cup away. Now, add some water, and what happens is this super absorbent gel absorbs the water and turns very quickly into a paste. Look at that. Now, let's max it out. 5 kilograms of super absorbent gel, 500 liters of water. Now, it is time to do science! And I have my own stir stick. Yep, definitely coming along. I'm not exactly sure if we're getting anything on this camera, but I want to make sure it's recording. Yep, it's recording. There we go. It is definitely turning solid. Well, there you go. The giant super absorbent gel experiment. Corey, Trevor, I need some help getting out. How many outfits have I been through in this episode? How many outfits have I been through in this episode? Anybody have a towel? There you go. Thanks, buddy. That's great.
Husnia's idea of adding structure to the tinfoil boat was definitely right. We just needed to go further. So we did it again. This time, we made a much larger boat. We started with a sheet of cardboard, then wrapped the tinfoil around and added some metal supports taped to the cardboard across the boat this way to make ribs, as well as some other supporting pieces in the front and the back. Then another metal rod all the way around the top, and finally, supports across the middle.
All right, feel how strong it is. I'm really excited about this version of the tinfoil boat. What we did is we used thwarts, big hard pieces of wood that we did last time, but this time we have ribs.
Ribs, right, which are made of a cardboard, a metal rod attached to it,
and shaped, and we did a whole bunch of them that go the whole length of the boat. And then we used all of this bendable metal, and we have one that runs all the way around the gunnels, and a whole bunch that run down the inside, and we even used bike fenders at the front and the back of the boat to give it super rigidity so that it hopefully won't go like all the other boats have done so far. Are you ready, Husnia?
let's do this.
1, 2, 3, lift. All right, let me get over. It floats, But that doesn't tell us anything because they've all floated at this point. It's only when I get into it. Okay, here we go. All right. Hey! Hey, it works! All right.
Oh, it's working.
Ha 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 ha! Look at that! It works perfectly! The tinfoil boat experiment has been done. Science Max, experiments at large. What do you think, Huzia?
The only reason I got into this boat because I knew it's gonna work.
Really?
Oh yeah.
So you knew you would never get wet? See, I don't think that's fair. I think it's time that you got wet. I think we should go. I think you and I should just get wet right now. Just need
Someone help.
You're still dry, aren't you?
Okay.
That is so unfair.
Hey, Science Maximites. Today, we're doing the egg drop experiment and oh no. Oh no! Ha 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 ha. Things like this egg carton are designed to cushion the eggs in case it accidentally gets dropped or in case you want to stack something on top of it. The egg drop experiment is a great way to design some really cool stuff, and it's easy to understand. You take an egg and you drop it. So, let's get designing our egg drop experiment. First, you're gonna need an egg. No! Why? Everything's fine. 1, 2. Right, so where were we? Yes, you need an egg. And you need an adult's permission just in case you make a mess. Now, there are 2 ways to approach the egg drop strategy. You can cushion the blow, or you can slow the descent. And there's tons of ways to do either of those things. Cushioning the blow, pretty easy. You get a whole bunch of soft stuff that the egg can fall into so it doesn't break when it hits the ground. Or slowing the descent, you do something like this parachute idea, and it slows the egg as it falls so it doesn't hit the ground with as much force. And you see, the egg is totally fine because it went slowly to the ground. Now, this episode isn't just about dropping eggs. It is about material science. The kind of materials that you use make a big difference. Styrofoam, tissue paper, very light plastic, very light string. If we were to say use different materials for our parachute version, say wood instead of styrofoam and heavy string and very heavy fabric, I wonder if this would work as well. No, it doesn't. So there you go, Science Maximites. Materials make a difference. And that's what this episode is all about. Material science. Cutting edge materials, new materials, and dropping a whole lot of things to see if they break. But first, I need an expert to help me. Let's see, who should I pick? Jenna from the Ontario Science Centre would be great at this. Okay, come on. Huh? Hey, Jenna!
Bill, how you doing?
Jenna from the Ontario Science Centre is gonna help me max out the egg drop.
Yes, but we're gonna need an egg, right?
Yeah, no, I had one when I came through the door. Whoa!
Woo! So do we have some more eggs?
No, that was the last one. But that's okay, because I think we should max out the egg drop, so we need something larger than an egg.
How about pumpkins?
Pumpkins, great idea.
And now we need somewhere to drop them from.
Oh, I already know that. We should drop it from up there.
I think we're gonna need a control group, a control pumpkin. if you
A
will.
control group. You need that in science.
Right, if we're dropping pumpkins and we have nothing to compare it to, then we can't make appropriate observations.
Right, so we just drop a pumpkin straight to see what happens.
Yeah.
Awesome, so we'll get a whole bunch of pumpkins,
Yes.
and we'll start building.
Yeah, let's do it.
And then we'll also probably need to clean this up. Wait, I got a mop over here. This is our control pumpkin. A control in science means a version you don't experiment on, so you can compare the results of your experiment. So this is what a pumpkin does when dropped with nothing to cushion the fall. Jenna and I really have our work cut out for us because a pumpkin has a lot more mass than an egg, which means it's going to be much harder to stop once it's moving. So now all we have to do is come up with a couple ideas to stop that from happening.
All right, let's do it.
Science. Yeah. You want the best material around?
Well, you come to the right place. I've got them all. I got you flubberoid, magnoplex, flexoweed, pastotherm, blooperfoam. You need hydrogelatinous substrate? I got it. But you know, all those fancy materials are nothing compared to the good old-fashioned spider web. Huh? Hey, where's Gary? Ramona, Gary got away again. You know, people ask me, Sal, is it true spider webs are stronger than steel? And I tell them, it depends. When you look at a rope or a thread or a fiber, you talk about its tensile strength or its ability to withstand force before breaking. But you're comparing different things, so you have to compare them by thickness. So if you're comparing a steel cable to a spider web of the same thickness, then yes, steel is stronger. But spider web is 6 times lighter than steel. So if you are measuring strength to weight, spider web wins every time. Gary! So why don't we build more things with spider web? Well, for one thing, it's sticky and difficult to work with. Almost finished knitting this spider web sweater. It's only gonna take me about 80 more hours. And it's not easy to train spiders. Okay, Steven, one long, non-sticky thread and you get a cookie, okay? And, hey, where's Marco? And Petunia? Huh? But no need to train spiders now because modern science has surpassed the spider web. Enter carbon nanotubes. Huh? This thread doesn't look like much, but it is made of tiny little tubes made of carbon atoms. Think of them like a straw, but a really long straw. Carbon nanotubes are incredibly light and strong. Remember when we compared strength to weight? Well, steel is heavy. Spiderweb is about 6 times stronger by weight, and carbon nanotube is about 50 times stronger than that. That's so great. So why aren't we making everything out of carbon nanotubes? I'm gonna knit a carbon nanotube sweater. Well, first we have to make them cheaply enough to be affordable. There you go, one carbon nanotube sweater. $480,000. But material scientists all over the world are hard at work trying to find ways to make carbon nanotubes faster and cheaper. And soon, they'll be everywhere. And then spiders can go back to spinning their webs in peace. There you are, Gary. Where's everybody else? With Petunia and Marco and... What do you mean they're in my jacket? Jenna and I are coming up with solutions to the pumpkin drop. We have 3 material science strategies. Strategy 1, polymers. Something is a polymer if it's made of long chains of molecules. Everything in this category is a polymer-based solution. Rubber and elastics are polymers, so I thought, what about a trampoline?
Look to the left a little bit.
My left or your left?
My left. Alrighty, here we go.
And it works great. The pumpkin totally survives until it lands from the bounce. That's it, like it's a success and a failure. Balls are made of polymers like rubber or plastic, so how about a bag of balls? There's the pumpkin. Whoa! I think that worked. Whoa, mostly unscathed.
Almost there, almost there.
Right. Bungee cords are made from elastics, which are a polymer. And it worked, I think. I mean, it stopped it from falling, but never made it to the ground, unless we unhooked it. Technically, it survived better than any other pumpkin, really. Here's another polymer solution. This is cornstarch mud. It's a liquid, but if you hit it, if you impact it, it turns rigid.
Right, so that could protect the pumpkin.
Oh, yeah. And now,
The rest.
we add more cornstarch. Cornstarch mud strategy. But it turns out hardening on impact doesn't cushion the pumpkin much. Yeah, a bit of a problem there.
I don't think this worked.
And every scientist's favorite polymer, giant tub of slime.
Where did you get a giant tub of slime?
Episode 6. All right, let's check it out. Little slimy, all awesome. Now let's recap. This is our control pumpkin, so solutions work if they do better than that. Trampoline? Yes. Then no.
Bag of balls. Yes. Bungee cord. I think we need to disqualify that one. Cornstarch mud. Barely. Slime. Yes. Not bad for our first round. Science! Advanced materials in 60 seconds. Scientists and engineers are always coming up with new and advanced materials. Some are for spaceships, and some are just for fun. I'll show you a few. Hold on. Like, oh, this. This is a thermochromic mug. It's cool right now, but if you add hot water, it changes color. Ooh, this spring is made out of nitinol wire. It's also called memory wire, and I'll show you why. The reason it's called that is because it's a metal that remembers its shape. This one remembers being straight. All I have to do is drop it in hot water and it turns back into a straight wire. How cool is that? Ha Science! Oh, this is ulexite. It's sort of a see-through rock, but it's made of perfectly aligned crystals. So it's not just see-through, but the image actually gets transmitted from one side of the rock to the other. Advanced materials are really cool. I can't wait to see what science comes up with next. Now it is time to talk about an amazing natural polymer. It is hagfish slime? Ugh. Still, well, hagfish, that's probably just an unfortunate name for the fish. I'm sure the fish itself doesn't. Ugh. Okay. So, hagfish makes slime, apparently. When a hagfish is attacked by something that wants to eat it, like a shark or an eel, it secretes a tiny bit of a natural polymer. That's this little white bit right here at the end of this test tube. Now, it doesn't look like much right now, but it reacts with seawater. Watch this. Hagfish slime is very interesting to scientists because you start with just a tiny little bit and add seawater, and suddenly you have a lot of slime. Whoa. This stuff is actually pretty cool. Hagfish slime is a natural polymer. It's made just the same as the other polymers out of long chains of molecules, but it's naturally produced by a living organism. And because it's naturally produced, that means it's biodegradable. Hagfish slime. It's pretty cool after all. Ugh. We've had some good successes with polymers. Whoa, mostly unscathed.
Almost there, almost there.
Right. Now it's time to try our foam solution. The first foam we use is fruit netting. Foam fist bump. Boom. See? That didn't feel like much at all. Which didn't seem like enough protection. Pumpkin ball. Pumpkin, actually, pumpkin sphere. Wrapping the pumpkin in a sphere of foam. Go pumpkin sphere! It worked better, but not perfectly.
Uh-oh. It split right down the middle.
Pumpkin cube!
Phil?
Yeah.
Phil, what is it?
Wrapping the pumpkin in a cube of foam. Better than our control, but you can see the pumpkin crush as it lands.
Oh, no. Phil?
Totally great! How much did it hold together?
Not at all.
I'll give it 3 cubes out of 7. We need more protection.
Pumpkin helmet.
Which leads us to a bike helmet solution. Which worked the best of all so far. Totally survived!
Oh my goodness!
Yes, I know, this pumpkin's a bit smaller than our control pumpkin, but our big pumpkins wouldn't fit inside helmets, and we figured it was only a fair test if we used a pumpkin the size of your head. This is why you wear a helmet, Science Maximites. Look at that. Unharmed.
Expanding foam sealant.
And we spray it all the way around the pumpkin. Expanding foam sealant is special stuff used to insulate gaps and cracks in the walls of your house. It comes out of a can soft, but then expands and hardens to foam. A full pumpkin completely covered in expanding foam! Turns out this stuff is made for insulation, not absorbing shock.
Our beautiful foam pumpkin.
I don't think it worked that well. So now we recap our foam solution. fruit netting? No. Foam sphere? Yes. Foam cube? No. Bike helmets? A big yes. The only perfect pumpkin yet. Expanding foam? No. So that's it for our foam solution.
I think we should move on to armor now.
Yeah, all right. Foam. Foam. Foam! How can they all be foam? Well, foam usually means something to do with bubbles. There's all kinds of solid foams out there, and they can be squishy or not squishy. And they're usually light. Air is an insulator. That means it does not conduct heat or cold very well. You see, I cannot tell this ice is cold until I get my finger really close to it. Yeah, there it is. There, I feel it. And because foam is full of air bubbles, it makes a great insulator. That's why we make coolers out of foam. So what's the best, most advanced foam out there? It's this. It's called aerogel, and it's 98.2% air. It is super light because it's mostly air, and it's a great insulator because it's mostly air. It's great to pack things in as well, and NASA uses it on the Mars rover and in spacesuits because it's such a good insulator. Cool. Or not cool because, you know, it's an insulator, so it would protect from the cool. We've tried polymers. Little slimy. All awesome. We've tried foam.
Uh-oh. It's split right down the middle.
Now it's time to try armor. Anything that protects the pumpkin in a shell of some sort. This does not look like armor, Jenna. This looks like pumpkin soup. Our first solution may not seem like armor, but it's a hard shell and the pumpkin floats in the water. When we drop it, the bin explodes, which slows the pumpkin down a lot. The result? Not perfect, but still, remember, it's better than our control. So compared to the control pumpkin, that did pretty well.
That was pretty good.
Yeah.
I'll give you that.
What is this?
All right, well, we've got a pumpkin covered in knee pads.
Knee pad pumpkin! Knee pads are armor for your body. So wrapping the pumpkin in knee pads... Knee pad pumpkin!
Drop it, Bill!
Didn't seem to make much of a difference. Maybe it didn't land on a knee pad. Maybe we just missed. It ended up in between the knee pads.
I think that must be it. It's looking a little rough.
But using sports equipment gave me an idea for using an advanced material. It's called sorbethane, and it's used in modern sports equipment. It disperses impact. See, watch this. Okay, so I've got a hammer, and I hit the pumpkin here, and it goes right into the pumpkin, right? So, take that. Now I hit it again on the sorbethane, and haha, see? Nothing. So I thought maybe this will cushion the impact. The result? Not bad.
I don't think it dispersed it quite well enough. There is a crack coming right from the hole that you made with that hammer.
Okay, so the hole might have structurally weakened the pumpkin a little bit. So the sorbethane did a pretty good job, actually.
Yeah.
Good thing it is in athletic equipment. That's what it's for. Carbon fiber is a very modern kind of material.
It's carbon meshed together and then glued down, so it's super strong.
Super strong, and the pumpkin is contained inside. It's like double shields.
Yeah, so can I test how strong this is?
Oh yeah, this is the armor solution, so let's try it out.
Here, better try it.
Whoa! But when we drop it, we realized there were too many hard surfaces. And not enough cushioning. But the carbon fiber held up really well. Slowing the pumpkin down and cushioning it is the answer, which leads me to my final solution. I call it the lunar lander. That's what I was doing. I was coming in, right?
Right.
Yeah.
See, I thought we were supposed to be doing armor?
Yes. So this is armor. I know it looks like foam, but you see armor like in a helmet, it's supposed to crumple to protect your head, right? So this will also crumple because it's not just foam, there's wood inside. So the wood is supposed to break and then the foam bends and the whole thing is supposed to cushion the impact of the pumpkin. Ooh.
That looks pretty good.
The landing crushed and broke a lot of the arms of the lander, but the braking cushions the impact. Oh, what do you think?
I think it's good. I think we're good.
Look at that. And now the awesome recap. Remember, the difference between doing science and just having fun is recording the results. Water bin? Yes. Knee pads? No. Sorbethane? Yes. Carbon fiber? No. Lunar lander? Yes. So, we've had some successes and a lot of failures, and we've learned a lot of things about different materials. And we have one pumpkin left. There we go, Science Max Experiments at Large. Pumpkin drop, thank you, Jenna.
Thank you, Phil, that was awesome.
And we still have one pumpkin left. Whoa, whoa, no, no, no! I got it, I got it. It's fine, everything's fine.
Fine.
We can
I got this.
Yeah,
It's
we can
fine.
take that up.
Yeah, no, it's
you got it, you got
good.
it. Careful. Oh, well.
Oh, okay, well.
Make that 0 pumpkins left. Greetings, Science Maximites. My name is Phil, and today we're talking about friction. I didn't slide.
Take 2.
I can't, I'm still not. Oh, I know. I got it.
Take 3.
Socks don't work any better.
Take 15. 34. Take 36.
I don't know why I thought that would work.
Take 52.
I'm Phil, and today we're talking about friction! Sorry, okay. Oh, friction! We did it! We got it, everybody! How many takes was that? Oh. Well, still, we got it. Good work. As you may have already guessed, today is about friction, and here's a really easy friction experiment you can do at home. All you need is a piece of wood. You don't need the frame, and you don't have to do anything fancy to it. Just put one end up on a couch or a coffee table and make a nice ramp. Then you want something to slide down that ramp, and I like to use a piece of wood. Now check it out. Wood ramp, wood block. The friction is so much that the wood slides to there. Now what I like to do is take a little flag and mark the results. Recording the results is good science. Now here's where it gets fun. Get another surface and attach it to the wood, like carpet and wood. Let's see how far this goes. Not as good. All right, record the results. Cardboard. Ooh, nicely done, cardboard. Foam. And this wood has been waxed, like on a floor wax, which makes it nice and slippery. Let's see how that does. Ooh. And now the ultimate ice attached to wood. This is actually harder to do than I thought. All right, let's try it out. Ice! The clear winner. Not a big surprise right there. And get this, once you've done all of that, you can change the surface of the ramp. You can go to waxed wood, carpet, foam, cardboard, well, yeah, you get the idea. Record all the results, compare them, and there you go. Friction ramp experiment. And that's what we're gonna be maxing out today. So come on, let's go. Check it out, I've improved the portal interface. Watch this. Yeah, and then I can scroll through experts, and oh, this is gonna be fun. And I've got my coordinates right there. Oh. That's never happened. Okay. Hey, Sarah!
Hey, good to see you again.
Good to see you too, Sarah. From Mad Science, you're gonna help me max out friction!
Yeah, friction.
What do you think of my max out friction room?
It's amazing. It's so wonderful. So how are we gonna max out friction today?
In the lab, I had a ramp, and I had stuff with different surfaces on it.
Oh, that's so cool. It's too bad you don't have it here. We could totally test that out.
I can bring it here.
Awesome.
I have a new app on my phone that talks to the portal. And let's see. That's not what I... Oh, hold on. Okay, there we go. And... Whoa. Well, I can do this. I just... it needs an update.
Yeah.
That's what the... Yeah!
There we
it
go.
is. Okay.
Perfect.
So here we go.
Amazing.
The friction ramp, it's pretty simple. You just take, I've got blocks of wood with different surfaces.
Amazing.
And then you just slide them down the ramp.
Right. So cool.
Yeah, so what if, to max it out, what if this is us?
We're a block of wood?
No, I mean like we are on the block of wood, and then we can try changing the bottom. I guess a block of wood isn't the right thing to use, though.
Right, yeah. Maybe we could use like a sled.
Oh, yeah, okay, like a snow sled. That's a great idea. Okay, so we'll tell you what. I will portal in a sled for us.
Are you sure you want to portal it in?
I'm sure. Just stand back,
Okay.
though. Okay. Ha!
Ah, there we go.
Maxed out friction slide! You ready, Sarah?
Yeah, I'm ready.
Okay, here we go.
All right.
Sarah and I pushed each other around on the sled, which was fun, but it was also tiring.
It's pretty hard. This is
My turn. My turn.
All right.
Oh, yeah! Whoa, friction! Yeah, friction! Yeah! Yeah, friction!
But we soon realized it'd be pretty hard to measure how much friction there was. You know how hard you were pushing?
I had no idea how hard I was pushing.
A lot, but that doesn't really help in science terms. So
Exactly.
what do we do?
Well, with your first experiment, you used a ramp. Could we maybe put a ramp up in here?
In here?
In here, yeah.
I guess.
Then we can measure also how far we go so we know how much friction is being used.
Right, so we have our control, and then we have all the, just like the blocks.
Exactly, just like the block.
Okay, great. So we'll get the ramp, we'll get a bunch of wood,
Yes.
we'll get some tools.
Yeah.
The case of the missing friction! It was rough all over in the big city. My toughest case yet, and I felt like I was getting nowhere. Someone stole all the city's friction. And it was my job to find out who and get it back. But after a week, I was no closer to solving the case. It was hard to get anything done now that there was no friction. Uptown to downtown, people were sliding all over with no way to stop themselves. It was chaos. Chaos, I tell you. But if there was any detective that could solve the case, it was me. But it's like my grandma always said, it's tough to follow leads if you can't sit in your chair. Nothing stays put in a city without friction. And you never appreciate something till it's gone. The phone rang. Sure, I wanted to answer it, but it slipped through my grasp just like this case. The mayor was on the line. He wanted to know if I'd made any progress. But I felt I was going in circles.
I'm gonna have to call you back, Mr. Mayor.
Without friction, you couldn't do very much at all. It was going to be my toughest case yet. Sounds good. Sarah and I are maxing out a friction ramp. Step 1, make a giant ramp.
There, are we done?
Hey, I think so.
We're done. But it proved a bit hard to lift up to the second floor. Fortunately, Sarah had an idea.
Maybe we could use this crane.
We use the crane!
Oh, yeah, I've got a 5-ton crane at Science Max headquarters. Good thinking, Sarah.
So we rigged it up and tried it out. The bonus was we could make the ramp any angle we wanted.
Okay, time to get my helmet, because don't go any higher than that, because I don't have my helmet. And then we will start sliding down. Friction ramp!
I got on the slide and Sarah lifted it up until I started moving. And that allowed us to record our results.
We're at 2 meters.
2 meters! Recorded! First recording done, now we switch it up.
We tried it again with Sarah on the slide to see if she slid at the same height. And she did.
Yeah.
Now we have a way to record the results. The plastic sled went down the ramp at this height. Things with more friction will mean the mark is higher, and less friction will mean the mark is lower. So then, we tried it with...
Cardboard! What did we get?
And it was...
A little over 2 meters.
Meaning?
Cardboard is a little bit less slippy than the plastic of the sled.
All right.
Ready for carpet sled?
Good to go.
Here we go. Oh, past 2 meters. Oh, almost 3.
Here we go.
Carpet had even more.
Oh my gosh, we're going this side.
Whoa!
That was so cool.
That was exactly 3. Then we tried foam.
Coming up on 2 meters. All right, coming up to 3. It won't go up any higher.
And just like the wood block, the foam didn't slide at all.
What if I like do this and then I slide? Right, so, friction sled on foam, highest friction of all of the materials.
Oh, hello there. Here's a fun science experiment you can do with science and friction together. Take 2 books, put them on top of each other, and pull them apart. Ooh, not too much friction. But if you take the books and you interleave some of the pages, maybe 3 or 4 parts, and try it again, pull them apart, they're a little harder to pull apart. That's because the friction for more pages touching each other actually starts to add up. So, what if we were to take 2 books with a lot of pages and very carefully and meticulously take each page individually, one at a time, and overlay each one and go back and forth? These are 2 books completely shuffled together. The elastic band is actually just to hold the covers together. All right. So, now the friction between all of these pages, when I try to pull it apart, makes it pretty much impossible. Now, there's 2 things going on here. First of all, when you start to pull the books apart, the pages start to stick together because they squeeze together, because you're pulling and they're squeezing. And the fact that there's so many pages sticking together, the friction builds up to a degree that is actually very impressive. But don't take my word for it, let's max it out. Here is another 2 books, elastic just to hold the covers. This one clamped to the wall, and I'm gonna pull on this one. Science! Still don't believe me? Well, let's max it out some more. 2 books, all the pages layered together, held together only by friction suspended over a giant vat of slime. Now, let's see how much faith I have in science. Friction! Yeah! Okay. Okay, oh no. Okay, now to get down. Okay, hold on. And then. Science! That was close. Sarah and I have used our maxed out friction ramp and compared the regular sled to cardboard and foam. What's next?
We've waxed the bottom of this sled, and we're gonna try a wax sled next.
Wax sled!
All right, here we go. Right.
1 meter.
Oh boy.
1.5 meters.
Whoa!
Wax sled! Woo! The slipperiest yet, only 1.5 meters.
That's awesome. Do we have anything that's more slippery?
Yeah, we do. We have ice sled. Are you ready to try it out?
So ready to try it out.
Okay, let's do it.
All right.
And
there we go. Whoa! That was awesome.
look how far you went.
That was so cool.
And only 1.25 meters.
Least amount of friction.
Ice wins. So I think we should do something else to max this out, though.
Maybe bringing it up a little bit more and using something with less friction.
Wait, I have an idea. Yeah, okay, come with me. This is a climbing frog. Why does he climb? Because of science. I pull on this rope, and then I pull on that rope, and I pull on that rope, and he climbs up the ropes. And why? Well, because of friction. The secret is 2 straws. The straws are pointed away from each other at the bottom. This allows it to climb thanks to friction.
Take a closer look. When I pull on one string, it pulls straight, which makes the frog pivot. That string slips through the straw because there's not a lot of friction. But there's lots of friction on the other side because of the angle. So one side of the string goes down, which makes the other go up, which means the frog goes up with it. All thanks to friction.
So now, let's max it out. This is a super maxed out climbing frog.
Just like the small version, I have a rope going through 2 tubes. I pull on one rope and the other holds on by friction. Then I switch.
And it does work. It's just a lot harder to pull on the ropes. But it totally works. Whoa, careful. Whoa. There, and then this one, and then that one, and then that one. Yeah! A giant climbing frog! All because of friction. Here's another way to defy gravity using friction. Get a plastic water bottle and fill it with rice.
Take 2.
So get a plastic water bottle and fill it with rice using a funnel. Then take a shish kebab skewer and stick it into the bottle and nothing happens. But if you tap the bottle down, the rice starts to pack in a little bit better. See how the level of rice is lower? Which means you can add more rice. Pack it down even more. And you can even use something the same diameter as the mouth of the bottle, like, say, a highlighter. And make sure all the rice is as packed in as you can get it. There. Now the rice is really packed in there. And when I stick the shish kebab skewer in, the friction between the pieces of rice and this wood is enough to lift the bottle using nothing but friction. Now, let's max it out. I filled this 20-liter water cooler jug full of rice, and it's really heavy. I wanted to see if I could lift it using nothing but friction and this dowel, which is just a round piece of wood. All right, here we go. Ah, science! I'd max it out even more, but I don't think I could lift anymore. It's okay, I can just fit. Newton's first law in 60 seconds. Newton's first law says an object in motion tends to stay in motion. So why don't they? See, if I was to throw this, it doesn't stay in motion, it doesn't keep going, it slows down and falls to the ground. Well, the whole law states an object in motion tends to stay in motion until an external force acts upon it. So what forces are acting upon this? Well, gravity for one, pulling it down towards the ground, and friction, specifically air friction, slowing this down and making it stop. Now, if you were to have something very light with a lot of surface area, it would really be affected by air friction. You wouldn't be able to throw it very far at all, no matter how hard you tried. So there you go. Newton's first law, an object in motion tends to stay in motion unless it's affected by an external force, such as friction, like air friction. So there you go. Sarah and I have recorded a lot of results on our ramp by raising it till we started to slide.
Here we go.
Now we've decided to raise the ramp to the highest point and see how far we can go using some low friction things, like a wheeled cart.
I've made a double bike cart.
Wheels are great for moving. They have rolling friction,
Ready?
which is different from sliding friction.
What happened?
You went through all those boxes back there.
That was it. We went really far. Total fun. Let's try something else.
So what are we gonna do next?
Now we're gonna do the frictionless, this thing that we have at Science Max headquarters, a hover disc.
Oh my gosh, that's so cool. Where did you get it?
Built it, season 1.
Amazing.
As you may remember from that episode, a hover disc uses air to greatly reduce the friction with the ground.
Here we go.
So what would a hover disc do on a ramp?
Right.
Only one way to find out. recap. Friction is when two surfaces rub against each other. You can have a very small amount of friction or a very large amount, depending on the materials. And using science to reduce friction results in the best sledding experiences.
Nicely done. Science, Max. Experiments at large. Your turn?
My turn? Yeah, let's
Okay,
do
so
it.
take those, and I'll get this, and then I'll give you the helmet. And then we gotta rebuilding the boxes is like the hardest part of this whole situation. But greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large. Whoa. Oh, I better spin the other way. Today, we're gonna be taking a closer look at spinning. Well, all things spinning. Spinning, rolling, rotation in all its forms. And, when things spin, they're subject to a whole bunch of different forces, and some are strong enough to even counteract gravity. So let's get spinning! Oh. Okay, let's get spinning! We are going to make a gyroscopic whirligig, and it spins, and I don't, which is a good thing. Watch this. You pull the string, and it spins, and it stands on its end.
Why does it stand on its end when it spins? Because of angular momentum, which we'll get to later.
And here's how you can make one of your own.
You will need some craft sticks, string, a small zip tie, a shish kebab skewer, spacers like these wood blocks, and finally some round discs, which you can cut out of plastic or find from parts of broken toys. Now, if you want to research this yourself, look up Gyroscopic Whirligig.
Get 2 craft sticks and glue them to your wooden blocks just like this, and then do it again.
Space them apart and glue them to crosswise craft sticks, and this will be your launcher.
You put your hand in the small end, and the longer end here is where you put your gyroscopic whirligig. Now let's make that. What you want to do is you want to take a shish kebab skewer or whatever fits the diameter hole of the round things that you're using. I like to use little plastic discs from, these are from remote control mechanisms, but you can use anything you want.
I found that this launcher works best with 4 discs of the same size.
Just like that.
Space them out evenly, glue them down, and cut the skewer even on both sides. Then add your zip tie. Put it right in the middle, tighten it up, and cut off the dangling end. This zip tie just gives you somewhere for the string to hold on when you wind it up. Now for your pull handle. Glue 2 craft sticks and 2 wooden blocks, then 2 more craft sticks on the sides. Then tie a string to the middle, wrap that string around the middle of the whirligig, and
aha! You have a gyroscopic whirligig, a pull handle, a rope, and your launcher. Now remember, you put your hand in like this, and you fit your gyroscopic whirligig in just like that, and you pull towards you, and it spins! Oh, and that's what we're gonna be doing today, Science Maximites. We're gonna max out a spinning rig, something like this. It's gonna spin bigger, faster, more weight. It's gonna be totally maxed out. So come on. But first I need an expert to help me out. So, let's see here. Wait a minute. Aha! Perfect. Come on, this is gonna be great. Okay, this is it. Hey, Silena from the Ontario Science Center. I'm really glad you're here. You're gonna help me max out the gyroscopic whirligig.
The what?
Oh, the gyroscopic whirligig. Here, I'll show you. It's this, and it spins, and what works on
Phil, where are your shoes?
I think these are my shoes. They must have changed into flippers in the portal. Weird.
Want to change them?
Yeah, I'll be fine. Anyway, like I was saying, the gyroscopic whirligig is really good. Let's do it here so that I don't have to walk as far.
Can I see it?
Yeah, here it is. Ready? You spin it up, and it spins, and it goes for a while, right?
Because you made it out of 4 discs, it probably spins better because there's more mass.
Oh yeah, because you know what? I actually have an old one. Yeah, I got an old one here with 1 disc, and it does not spin as long as the 4-disc one.
Could we test the 1-disc one out and compare it to the 4-disc one?
You bet, because you know what that is?
Science.
Yeah, that's science. Okay, let's try it. Ready? Whoa.
Huh, look at that. The 4-disc ones spin better longer than the 1-disc one because the 4-disc one has more
mass, therefore more inertia. So when we max it out, we should get something with a lot of mass.
Yeah, more mass.
Wait, I have something. Right. Well, can you give me a hand?
Careful, Phil. I don't want you to fall.
Yeah, well, I don't want to fall either. It's hard to walk in these.
I can imagine. That's why I asked you if you wanted to change your
Nah, we're
shoes.
fine. I'm fine. Okay, check it out. This is what I was going to. Okay, this is what we can make it into our maxed out spinning gyroscopic.
I don't think it's gonna work.
Why not?
It's just, look at how big the hole is.
Oh, yeah, because we're going to need something to be the axis, huh?
Yeah, we need like a tree to fill that. I don't
Yeah,
think
you're
it's
right.
gonna work.
Too big. Is there anything else wrong with it?
It's also kind of light. It's not that heavy.
More mass, better.
More mass.
Okay, tell you what. Oh, I know. Hold on. I know. Whoa.
Oh, that looks perfect.
Yeah, and then we got this pole.
To go through the center?
We'll go through the center like that.
Awesome.
And then we'll just weld it together, and there you go.
This will be great.
Yeah, high five.
Phil.
Okay, no, wait, sorry, yeah, you got the thing.
High five.
Well, now I got the thing.
Yeah.
All right, I'll get new shoes, and we'll work on our high five. Now it's time for one of my favorite scientific terms, the Magnus effect.
I am Magnus, and behold my effect.
No, the Magnus effect has to do with things that are spinning. Things like these cups. And here's a great little Magnus effect flyer you can make at home. It's super easy. Get 2 styrofoam cups and tape them together at the bottoms using science tape. Then get some elastic bands and make a long one by tying them together. Take your elastic and you wrap it around the cup like this. Then hold the elastic on the bottom, remember, like that, and then let them go. They fly up and out. The reason why it goes up and stays in the air is because it's spinning, creating moving air over the top. Moving air has lower pressure, which means it's pushed up by the higher pressure underneath. And that is called the... Oh, come on.
Now, the Magnus effect.
Yes. So, let's max it out.
Magnus it out. See how much better that sounds?
No. Max it out. Check it out. Magnus Flyer 2.0 stand elastic slingshot. Wrap it around. Remember, for the Magnus effect to work, your cups need to be spinning this way, the front side rotating up. Oh, and there you have it, the Magnus effect.
I, Magnus, am now taking over the show. It is now Science Magnus. That is my effect, slightly improving the name of science TV shows. Science Magnus.
Silita and I are maxing out our spinning top. Based on our small version, we decided to make one with as much mass as possible. So we got a 20-kilogram weight and welded it to a metal shaft. Will this work the same way? Well, let's look at the science. Why does a top spin? Well, let's start with Newton's first law, which is an object at rest tends to stay at rest, an object in motion tends to stay in motion. But the in motion has another part. That object also wants to go in a straight line. If you think of a bowling ball rolling along, it would need another force to act upon it to make it change direction. We say that a moving object has momentum. Now, a top doesn't go in a straight line, it spins around, but it still has momentum. It's an object in motion, and even though it's spinning, it still does want to go in a straight line. It's just that that straight line is here. We call this angular momentum. To make a top move this way, or that way, would take an outside force, so it stays upright as long as it has enough momentum. But when it slows down, there's less momentum and it becomes harder to resist external forces, like gravity, which will eventually want to make it topple. Our top has a lot of mass, which means it'll have a lot of angular momentum when it gets spinning. It's just a matter of getting it spinning fast enough. So should we spin it?
Yeah, let's spin it. Let's see if we can get it to work. Hey, okay.
Spin.
Oh, we're gonna let go. In 3.
Wait.
wait. I can't get it.
What?
Wait.
Okay.
Okay. Not fast enough.
We need something to help us get it spinning faster. Maybe a rope?
A rope, yeah.
Wrap a rope
That
around
was
it
my
like the-
idea too, a rope, because the small one uses a rope.
Yes.
Okay.
Okay, I'll go grab a rope.
So, wrapping the rope up.
I'll let you wrap the rope
Okay.
up. I'll get my holder back on top.
Spin it counterclockwise.
We attach the rope and wind it up.
You want to make it super clean. This is some of the best coiled rope I've ever seen. I'm gonna pull the rope. You're gonna hold on to it, but I can't pull really hard because you won't be able to hold it up. Because we don't have to pull hard. We just have to get it going fast.
Yes.
Silita keeps her hand on the block at the top, and I pull.
Ready?
Wait a minute. We'll get all the way. Oh. Whoa!
Spinning a lot better than I thought it would. It's still spinning, but it's wobbling.
Oh, careful.
Oh, there it goes.
It works, but just barely.
It might spin better. It might spin straighter.
Yeah.
If we had it spinning, something help us spin it faster.
Yes. Faster with more power.
With more power.
This is a string. You can pull a string, but you can't push a string. Well, you can. You can push a string. You really can. Okay, quit it. Quit it. This little contraption works sort of like a baseball pitching machine, but in miniature. See, there are two motors here, and the wheels spin together to shoot things out this way. Things like this craft stick. Watch this. Whoa! Let's watch that again. Whoa! But now, watch as I put a large loop of string through. What? Pushing string. How does this happen? Hello?
I don't suppose it's the Magnus effect?
No, it's not the Magnus effect.
No, it's all right. I'll be in my lair if you need me.
Okay, right. Bye. Right, where was I?
I believe you were at, the reason why this works is...
Right, pushing string. How does this happen? It's all because of inertia. Check it out. The wheels are pushing the string through fast. It's got some weight, and it's got some speed, which means it has some inertia. So when it goes this way, it wants to keep going this way. But it goes all the way to the end, and then, because it's a loop, gets sucked back in this way, which means all of this inertia, you can sort of overcome gravity. Pushing string. Science.
Silita and I need to get our maxed out top spinning faster. We tried a rope, but now we're trying a drill. We get a wheel on our drill and use it on the outside of the weight to get it spinning up.
A little faster.
Oh, it's wobbling now.
A little more.
Okay.
And release.
Whoa!
It's kind of cool that it wobbles that much and it doesn't hit the ground.
It worked better, but there's always a way to max it out even more.
You know what we need, Silita?
What do we need, Phil?
A maxed out drill. Put it right on the top here and get it spinning very, very fast. Super maxed out gyroscopic whirly gig. Is it just the top now?
I don't know. Do you
We
want to
could
be
call it a
gyroscopic?
gyroscopic. Well, it's sort of a toppy, kind of gyroscopy. This is a bike tire. It's pretty light, but I still can't hold it from the end of the pole like this with one hand. Nope. But I can if I get it spinning fast enough. I just use this drill, and then I get... Okay, so this is gonna be awfully hard to do with one person. Oh, this is the perfect opportunity to use the Trevor button. Trevor button. Hey, Trevor from the Science Max build team. What are you doing?
Maxing this out.
Oh, right on. Can you give me a hand for a second?
Sure.
Awesome. Okay, so you take this drill, and we're gonna get this wheel spinning really fast.
Okay. I don't know if it's,
No, I don't wanna know.
I don't know if I remembered to...
No, it's fine. Max it out. We gotta max it out. So, because it's spinning, I can hold this heavy weight in the air.
How is this possible? Because the wheel is basically a top. The forces that prevent a top tipping, angular momentum, are still working here. This angular momentum resists a change in direction this way, which is how gravity would want it to tip. Interestingly, these same forces also keep it spinning around me in a circle.
So, I can lift a heavy weight in the air just by spinning it. Awesome max out experiment, Trevor. Yeah! What was that?
It's my science confetti high five I just made.
Well, you know what we should do?
What?
We should max it out. Yeah, we can make a giant one and then a whole bunch of confetti in it, and then people like jump up and do more confetti that would come out, right? And then so what would happen is there would be all this Trevor?
Silita and I have maxed out our spinning top. The trick is getting something that heavy to spin really fast. We've tried a rope and a drill, but now we have a maxed out drill.
So more power and more speed, which is perfect for spinning this massive top.
Yes, and perfect for maxing out anything.
We get it spinning and it works great. The top spins for a really long time. In fact, its mass was so large, it started drilling a hole in the concrete floor. We tried it again, but started to notice something.
The drill is smoking quite significantly.
Our drill began to overheat. Why? Good old Newton's first law. An object at rest wants to stay at rest, and an object in motion wants to stay in motion. The more mass we have in motion, the longer it will stay in motion.
This will go forever. Well, not forever,
Well, not
but
forever.
it'll go a really long time because it's got a lot of weight.
But that same mass wants to stay at rest when it's not moving. We have to overcome all that mass wanting to stay at rest to get the top spinning. And even for our maxed out drill, that was a tough job. But once it was spinning, there was only one thing to do. Max it out even more! Silita and I come up with a plan to max out the top by riding it.
You want to ride the top?
Of course I want to ride the top.
We can both ride the top. One person's gonna have to drill this, so we'll have to take turns.
Max Historica. This is Leonardo da Vinci, one of the greatest scientific minds the world has ever seen. And this is a wheel. Da Vinci thought to himself, wouldn't it be great to design a wheel that kept spinning forever? So he got to work. Something that keeps spinning forever without stopping is called a perpetual motion machine. And it was an obsession of Da Vinci's. Why, this is great. The bottles tip the water to the outside, making one side of the wheel heavier, which will keep it spinning forever. Except it doesn't work. You see, what Da Vinci doesn't know is that science says a perpetual motion machine is impossible. But of course it wasn't for another 350 years till scientists figured that out. So we can't tell Da Vinci. What? Oh, never mind. Leonardo da Vinci, one of the greatest inventors ever. Even if not all of his inventions worked. Silita and I got our maxed out spinning top to work pretty well. The only thing left to do was to ride it. We attached a large disc and a Lazy Susan. That's a platform that spins around on ball bearings.
Lazy Susan on top,
Lazy Susan.
so that you can ride on it.
Yes, and then we wanted to add this extra bit. Now, why did we want to add this?
We need a little bit more weight on our top.
Okay, so who gets to ride it?
I feel like you should ride it.
I think you might be right.
Because I want to use
Oh,
the drill.
the super awesome maxed out drill. Okay, so let's do it. First thing I should say is do not try this at home. We are trained scientists.
Silita uses the drill to get it spinning while I hold it steady. Then I hold on to our safety line above and carefully rest my weight on the top. It works, but not for long. We take turns trying it out, but it seems we have another part of science working against us. Good old friction. Friction with the air and with the ground is what eventually slows a spinning top down. But our weight on the ball bearings of the Lazy Susan really increases the friction. More friction means the top slows down a lot faster.
Whoa!
That was pretty cool.
It was kind of terrifying, right?
Yeah.
Good old Newton's first law kept the top spinning, angular momentum kept it from falling over, and friction slowed it back down. The forces were always the same, no matter if it was a little top, a maxed out top, or a rideable one.
Yeah! Whoa. There you go. Science Max. Experiments at large. Giant spinning top. That's as large a spinning top as I think you
I think in the entire world.
Let's do it again. Yeah!